Welcome to the CFE Media and Technology Virtual Training Week education session, Back to Basics, Electric Motors. I'm your moderator, Amara Rozgas with CFE Media and Technology. In keeping with our CEP policy, please take some time to read this quality assurance slide. This session is designed for technicians and engineers who want to understand the fundamentals of electric motors. Here's a list of the learning objectives. We'll touch on these in today's presentation. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. And here's some information about obtaining approved PDHs for today's session. If you're also interested in receiving one AIA CES approved learning unit for this event, you need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, you can access all this on the left side of your screen. The quiz will open up in a separate window, so please open it if you'd like to take this quiz. And it will end when this session signs off. In keeping with the American Institute of Architects Continuing Education System Policy, please take a moment to read the quality assurance slide. And for a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you'd like to take notes within this session, click on the left panel labeled Notes to do so. If you'd like to watch this on demand, then you can come back at any time. You can obtain continuing education credits by passing an exam at the end of this course. You must get 8 out of 10 questions right to earn 1 learning unit or 1 professional development hour. All right, well, I'm excited today to work with Jeff Thomas with Lockwood, Andrews, and Newnham. Jeff Thomas is Vice President and Business Group Director with Lockwood, Andrews, and Newnham, based in Houston. He's an electrical engineering expert with 28 years of experience as a project manager, energy manager, auditor, and certified healthcare constructor. He has presented on other electrical topics with Consulting Specifying Engineer, and he's a top-notch educator. Please enjoy this tutorial. Jeff, let's get started.
Thank you, Amara, and thank you everyone for joining. So today we want to talk about motors, and let's start with some basics. What is a motor? Well, according to the dictionary, it's got a couple of definitions. And the one I think we're most interested in is the last one. It's basically a rotating machine that converts electrical energy into mechanical energy. We see them everywhere. Everybody knows them. And here's some pictures of some different types. The one on the lower left is the little DC toy motor that a lot of us played with when we were kids, all the way up to the large number 6 running a vertical turbine pump in a wastewater plant. They come in all sizes and shapes, different configurations, different ways to run them, different ways to control them. This is a very large vertical turbine pump. It's a medium voltage motor, and it's moving a lot of water. It's a 3,500 horsepower motor running at 4,160 volts. So you can see these become very large. That particular motor was only running at 600 RPM, by the way. So let's back up. Let's do a little bit of history about motors and how we got to where we are. In the beginning, we had these great pioneers, Faraday, Tesla, Watt, Edison. All of these folks were trying to move us from the steam era into the modern era. Little history. 1831, Michael Faraday figured out that when he moved a magnet around a coil of wire, he got a current in the coil. This was big stuff back in the day. And he practiced with that and fooled around with it for quite a while. And then he decided, hey, I'm going to put this on a wheel that I can spin and get a more useful result. And I'd like to think that as he was doing this, he was thinking way ahead and saying, you know, I could run a steam engine to spin this thing for me and generate electricity. And as such, he developed the first direct current generator, sometimes referred to as a dynamo. And behind every good scientist is an assistant. And I'm sure his assistant one day said, hey, this magnet's got two ends. Maybe we should use both of them. And lo and behold, Faraday came out with his equation for electromagnetic force, which, as you'll recall from your electrical theory class, basically says the electromotive force around a closed path is equal to the negative of the time rate of change of the magnetic flux enclosing the path. And at the end of the day, basically what that means is if you move a magnet around a coil of wire, you'll get electricity. What he also discovered is that the frequency of the sine wave generated is a function of the speed and the number of poles of the magnet. When he started, of course, he only had two, but that relationship stays with us today, and we'll talk about that some more. So it got really exciting between the mid 30s or the mid 1800s and late 1800s. Europe got on board; they got electrified. Thomas Edison electrified New York, and if you really want some very interesting history, if you're ever in southern Michigan and you can go by Greenfield Village, you can see Edison's original invention for generating electricity to provide lights all throughout New York. And lo and behold, George Westinghouse comes on board and he challenges Edison for the best way to proceed. Because Westinghouse was convinced, and he had Tesla in his camp, that we should use AC distribution instead of DC distribution. Because Tesla showed that we can transform AC, but we can't transform DC, so we can transfer our electricity much farther distances than Edison could with DC. So in late 1800s, Westinghouse won that battle, and we went with AC distribution like we have today. However, back then, there were no standards. Prime movers were typically steam engines, and they were wildly variable. Whatever anybody had is what they used. Reportedly in 1918, London had 10 different frequencies of alternating current power, because a 2000 RPM steam engine producing 133 and a third hertz power was very common. And remember, at this point in time, the only thing we did with electricity was run lights. So we didn't really care about the frequency for the most part. Again, across the pond, slightly different. Europe began at 40 hertz, but then someone discovered that the lights flickered enough that we could notice it. So in late 1800s, Europe standardized on 50 hertz because 50 is metric friendly, and allegedly 60 is not a preferred number. And so Southern California jumped on that bandwagon, and they were originally at 50 hertz. The United States, for whatever reason, standardized on 60 hertz in 1948. Okay, so this is how we got to where we are. And remember, at this point in time, all we've got is lights. In fact, if you look at the history, the Edison Power Company was really the Edison Lighting Company, because that's all they did was provide lights. We didn't care about motors, because it wasn't until 1887 that Tesla came up with the first commercial, excuse me, induction motor. Two-phase current, phases are 90 degrees apart, and we have a motor. Didn't do a whole lot with that motor, other than, developed it. In 1889, a Russian gentleman, I'll leave you to pronounce his name, he invented the three-phase induction motor, because we all know three is better than two. And his invention pretty much set the standard for AC motors moving forward. So we got two types of motors we want to talk about. Actually, two main classes of motors: direct current or alternating current. And they both have uses, and they both require choices. So let's talk about DC motors for a moment. What DC motors typically do well is they have a much higher starting torque. They're quick starting and stopping, often used for stepping motors, control motors, things that require very precision movement. They're very easy to reverse. Switch the polarity on the leads, and the motor typically runs backwards. We can control their speed by adjusting their voltage, which is usually simpler and cheaper to control than an AC motor where we have to modify the frequency. DC motors have been entrenched in the control space for a long time. For those of you familiar with mechanical actuators, you know, they were pneumatic for many years, and then they got replaced with high torque, very precise DC motors for damper control, valve control, and those types of things. And I say they're emerging markets in automotive drives. In reality, we all know that DC motors have been in cars forever. The starting motor on your vehicle is DC. The motors that run the windows up and down is DC. If you have electric windshield wipers, it's a DC motor. So DC motors are very well entrenched in the automotive industry. Where they're becoming more pronounced is the makers like Tesla, Nissan, the folks that are making electric cars are using them to drive the vehicle in ways that we never thought of before. Also, as solar becomes more and more prevalent, we can use that DC directly in applications rather than transform it to AC, depending on our application. So what do AC motors do very well? Well, first of all, they're very reliable. They've been around forever, since 1887. And they have been modified, adjusted, tweaked, fiddled with for all that time. And they've been around, and they've been around, and they've been around, and everybody knows them. They're easy to maintain, not a lot of moving parts, really, if you think about it. It's just the armature that spins around on some bearings. They have a very large installed base. They're easy to find, okay? And they match the existing infrastructure. Because if you think about it, the infrastructure was sort of developed with the motor, and the motor developed with the infrastructure, and AC induction motors are kind of the thing. The issue, if you want to call it that, is we vary the speed with frequency. And that is a little more complicated, which is probably why VFDs, or close control devices, took so long to develop. Within AC motors, and we're going to really focus on AC motors because most of us are working in the commercial space, commercial building space, and even in industry and pump stations and water plants and wastewater plants, we're still all going to be AC type motors. But even within that space, there's another divide, and that's induction motors versus synchronous motors. All induction motors, which is what Tesla invented and what we're most familiar with, are considered asynchronous. And what that means is the rotor current is induced by the stator current, hence the name induction motor. But because of that, these motors will slip, or they have a component called slip, and we'll talk about that a little bit more later. Additionally, because of that slip, and because of the way these motors run, they operate at a lagging power factor. Everyone remembers power factor, and we'll talk about that a little bit more. The power factor, for the most part, is okay, but it can be our enemy. And again, we'll talk about that here in a few minutes. The advantage to induction motors is they're less expensive to manufacture and maintain. Again, like I said, very few moving parts. And since we've been manufacturing them for 200 years, we know how to do it, and we do it very well. And like we said, most of the motors in commercial applications are induction motors. There are, of course, exceptions. Synchronous motors, the rotor current is supplied in a variety of ways, but it's not by induction. And on a synchronous motor, the rotor turns in sync with the stator frequency, so there's no slip. All right, and that's important because now we can use these motors typically in a variety of ways, but for very small horsepower, synchronous motors are used for precision control or timing. If you're as old as I am, you remember your school actually had analog clocks on the wall. And if you ever wondered how they got all those clocks to read the same, it was through little synchronous motors. And they tied them all together and they managed the frequency, and then they could adjust all the clocks to read the same thing. Synchronous motors of any significant size typically have a higher first cost, which is why we don't see a lot of them. They're more energy efficient, however. So if we stop and think about the total cost of ownership, maybe we can overcome that first cost and use a synchronous motor. The big advantage is they're designed to operate between unity power factor and a leading power factor. So this is an opposite to an induction motor, which we can take advantage of. And we'll talk about that moving forward. So here's a graph I just put together just to kind of give us a spectrum of the sizes of motors we see in the world. And this is not meant to be inclusive at all, but it just kind of gives us a feel for, the sizes and what they do. If we start at the far left-hand side, in a commercial building with a water system or exhaust fan system, we'll see very small motors, just used to circulate water, exhaust fans in restrooms. They can be sub half horsepower, below 1 horsepower. And then as we move to the right, we see the things we typically run into. We see supply fans and exhaust fans. We see domestic water pumps, a jockey pump on a fire pump system, the fire pump system itself. As we move more to the right, we see small commercial water distribution. How are we moving water around in a plant, in an industrial plant, in a small area? Moving even into regional water distribution. The pump I showed in the video would be the 3,500 horsepower motor all the way over here, sort of far to the right. And then just for perspective, I threw a couple other little things in there I thought were interesting, is a couple of electric vehicle models and where they land, where they're purported to land. And then way on the right, just for perspective, the bow ship or the bow thruster on a cruise ship is about 7,500 to 10,000 horsepower. Okay, that's a big motor, right? But this just kind of gives you a feel for where motors are in the space. For those of us in the commercial building space, we're in the left-hand half or even the left-hand third of this chart. As we move to the right, it becomes more specialized applications. All right, so anybody who's ever had to replace a motor on an old piece of equipment has run into this. You get the new motor, you get it out of the box, you take the old one off the air handler, you put the new motor up there and all the holes are gone. What do we do? How do we deal with this? Fortunately, in 1926, an organization called NEMA was created. And what NEMA does is they try to standardize all of this stuff, okay? They don't like to use the word standard, but they really do develop standards. They are not an enforcement agency. They have no direct control over any manufacturer. But what they do is they help the manufacturers make things that are interchangeable, and they help the manufacturers rate things in a way that makes it easier for us engineers to figure out which one of the many hundreds of choices we want. So NEMA talks all kinds of things, and I'm going to cover some of them here, but by all means, this is not all of them. So let's talk about frame sizes. Frame size basically ensures the holes are in the right place. If you get a NEMA frame size, pick your favorite one, A, it's going to fit any other NEMA frame size A. The horsepower may not be the same. It may be induction, it may be synchronous, it doesn't matter. As long as the frame size matches, the holes will be in the right place. We have motor classes. Okay, this one's a little bit more important for us when we're specifying new equipment. There are currently 5 classes, and they're based on starting torque and the ability to accelerate loads. Sometimes we don't care, especially like in an air handler situation. The starting torque is pretty low, and we don't really care how fast it starts up. If it takes 30 seconds or a minute, we don't care, because typically in an air handler, once it's running, it's running, okay? And I say there are currently 5 is because as the industry changes, NEMA changes with the industry and adds classes as necessary. So real quickly, class A, extremely high efficiency, extremely high full load speed. They're very rare. They're so rare, I didn't even have a picture of one. I'm kidding. Motor class B, this is more typical, normal torque motors, low starting torque, typically on pumps and fans. It's not a huge locked rotor current type situation. Here's a pair of chill water pumps. I think these are about 5 or 7.5 horsepower. C and D are much higher starting torque. Positive displacement pumps or compressors. Air compressor starts against, in most cases, it starts against a higher back pressure. Large pumps where you have big head differential, the pump is going to take a little bit more torque to get started. So you may use a motor class C or D. This is a larger pump driving a water or larger motor driving a water pump in a water plant. And then there's E, which is the high efficiency version of B. And this would just be something where if we wanted to look at total cost of ownership, save a few dollars down the road by spending a little more up front, we might consider a motor class E instead of B. All right, sidebar on efficiency. As with everything in the world, there is no single standard efficiency testing method. Okay, there's 5 we show right here. IEEE is a good one, IEC, CSA, JEC over in Japan, and then BS 269 in British. So just throw that out there just for when you look at motor efficiency, just realize that depending on where your motor comes from, they're not all tested the same way. And that'll become important here in a minute. All right, now where are we going to put our motor? What kind of enclosure does it need to have? Is it going to be a wet environment? Maybe we want open drip proof. Does it need to be fan cooled? Can it be fan cooled? It'll probably run a little better if we keep it a little cooler. So maybe we use totally enclosed fan cooled. We have non-vented in case we have an environment where we don't want particulates in the motor. Okay, we have totally enclosed air over. That's a slightly different version of the TENV. Totally enclosed washdown. Obviously, that's for a very wet environment, like a washdown room at a food processing plant type of thing. Explosion proof. You're doing a grain elevator, a flour storage bin, so on and so forth. You don't want your motors, you don't want anything getting out or in. And then if we go into hazardous locations, we have class 1, 2, and 3. Again, more things that we need to think about as we're selecting a motor. Now we can talk about the design letter. And this refers to the locked rotor energy per horsepower. Okay. And this is a range value. So if we have more locked rotor energy per horsepower, then we're going to be a high letter versus, a low letter. This is important for us to know what, as we're designing, if we're designing an application where we're actually specifying the motor tied to the piece of equipment and we know the characteristics of the piece of equipment, we may have to modify our motor locked rotor starting conditions. This number would be important. Duty cycle. Depending on who you ask, there are between 4 and 10 choices, and I think this list changes almost on a weekly basis. What we're most likely to run across is what we call continuous duty. You start the motor runs forever. You don't ever shut it off, or nearly shut it off. There's a short duty cycle motor. Again, that's a rapid stop, start kind of thing. Periodic, it starts every 5 minutes and stops every 5 minutes. All the way down to what we used to call inverter duty. And inverter duty motors were born out of the variable frequency drive era. And what they learned, and it's kind of outside the scope of this discussion, but what they learned back in the day is if you have to, when you modulate the frequency, you have to keep an eye on the voltage or you can get unusual heating in the coils of the motor. So they came up with this slightly beefier version of a motor and they called it inverter duty to withstand those types of forces. I think most nowadays, every motor can tolerate VFDs, so that's sort of been adopted as a standard. So you may or may not find inverter duty specified anymore. There's something called a service factor, which I like to call the fudge factor. And that's really just a multiplier that the manufacturer puts on the motor that says for some specified or unspecified amount of time, you can run this motor at 15% over the rated value. So that would have a service factor of 1.15. Or if you're never going to run your motor up near the top end, you just get a 1.0 service factor and don't worry about it. These are related to something called the insulation class, and there's class A, B, F, and H. What this refers to is the type of insulation they put on the wiring inside the motor. Essentially, if you remember back to your wire sizing calculations in the NEC, it's not a conductivity problem, it's a heat problem. And motors are the same way. We have to be concerned about the heat. As we run the motor through its various stages, our insulation has to be able to survive the heat. All right, we talked about slip before. We mentioned slip before. So let's talk about it again. In an induction motor, we said the rotor lags the stator by some amount due to the physical characteristics of the motor and the fact that it's an induced event rather than a direct event. And this lag, or this, is called slip. And quite simply, the speed of the rotor is, or the frequency of the rotor, or the speed of the rotor is the frequency of the stator times 1 minus the percent slip. Slip is typically inversely related to the horsepower of the motor, ranges from 5 to 1/2%. 3% is very common, right? And the reason we bring this up is it's important because we look at a motor and we say, oh, that's a 4-pole 60 hertz motor. It's going to run at 1800 RPM. No, it's really not. And this is why. Because when we revisit that calculation, we got to take in the slip, the account for the slip. So the calculation used to be, or is, 120 times the frequency of the rotor divided by the number of poles. Well, now when we add the slip into this calculation, we have to modify our numerator, which changes our RPM. So 15 horsepower, 4-pole motor, 60 hertz, 3% slip, it doesn't run at 1800 RPM anymore. It runs at 1750. So why do we care? Well, we care because if we're specifying a motor to run a fan or to run a pump, the mechanical engineer or the hydraulic engineer is expecting that fan to deliver a certain flow, and that flow is directly proportional to the speed of the fan. And that 50 RPM will move us on the fan curve or the pump curve. May not be significant, but then again, it may be. So it's just something to be aware of. All right, related to slip, power factor, and efficiency. We talked about power factor briefly. And as you recall, we have real power, which is measured in watts, and that's what does work. And then we have apparent power, which is measured in kVA, and that's the amount of energy we have to supply. And then there's reactive power, which is the part we lose due to the inductive reactance of the motor. Couple of analogies. One analogy I've heard is this is like ordering a beer at a bar. The glass represents apparent power. The actual liquid beer is the real power, and the foam or the head is the reactive power. Okay. Or if you prefer, you could use when you go to the drive-through and get a soda, you know, the glass or the cup is apparent power, the ice is reactive power, and the actual drink is real power. So it's just some ways to think about it. And then power factor is simply the ratio of the real power to the apparent power. And unity power factor, or power factor of 1.0, would be ideal, because that would mean the real power and the apparent power were the same, and we're not losing anything through reactive power, sometimes referred to as VARs or kVARs, which stands for volts amps reactive. Why do we care? Again, poor power factor has costs. If we have to create a larger infrastructure for larger apparent power because our power factor is poor, we incur those costs: larger switchgear, larger wire, larger connectors. Okay. Because of this, it actually trickles all the way back to the power company, and they have increased generation requirements because they're generating a lot more energy because we're wasting it in volt amps reactive because of our high power factor. In some cases, depending on where you live, utilities will put a penalty on power factor over or under a certain amount. A lot of times it's 85%. Some places I've seen it as high as 90%. If you don't have better than 90% power factor, you get hit with a penalty on your utility bill. So it can be real money. Additionally, you can get heating on the neutral conductors, which increases your air conditioning costs. And again, anytime we heat up electrical equipment, it reduces its lifespan. It just doesn't like that. So we talked about every induction motor adding inductance to the system, which adds to the lagging power factor. So we need to correct that as opposed to just paying for it. We can do that one of two ways. We can add capacitance, which, as you'll recall, is the inverse of inductance, or negative reactive power. Or we can add or convert to a synchronous motor, which provides a neutral or leading power factor. It's pure economics at this point, okay? If you're responsible for operating the facility, you're going to want to do an economic analysis and say, it's cost me this much to do this much to do that. It's not a technical decision really at this point. efficiency is different than power factor and slip. They're related, but it's different. And as we recall, back to the basics, work output equals work input minus losses. So for every horsepower of output, we need 746 watts plus whatever our losses are. So NEMA is going to help us out again. There's types of losses in motors. There's primary and secondary resistance losses. You should remember the basics, power equals I squared R, okay? There's iron losses or flux losses as the magnetic field runs around the iron. There's stray current losses, harmonics, circulating currents in the rotor, etc. There are mechanical losses, frictions in the bearings. Do you have a fan? You know, the fan requires energy to turn and move that air. All of these things add up to costs or losses in our motor. It's very academic and difficult to try and calculate all of that, okay? Especially the current losses and the iron losses, because those are all a function of speed and horsepower and load, et cetera, et cetera. So NEMA jumps in and says, well, I'm going to give you some classifications. I'm going to give you standard, energy efficient, and premium. And if your motor wants my NEMA stamp of approval to fall into one of these categories, this is how it must perform. And you'll see that the higher the horsepower of the motor, the more efficient we want it to be. And again, now it becomes a life cycle cost analysis or an economics discussion. Because if I need 15 horsepower, whether I do it in standard, energy efficient, or premium, from the work perspective, I don't care. I'm still getting 15 horsepower. What I care about is how much is it going to cost me to get that 15 horsepower. A side note on motor efficiency, it only applies to 600 volt or lower motors. What NEMA has to say on medium voltage and high voltage motors, essentially they say they're complicated enough. We don't want to stick an efficiency category on them because that would just make it, you know, intolerable. So we don't worry about it for anything in the medium voltage space. So how do we start these things? How do we control them? Well, we have motor starters, we have motor controls. And now we get to talk about the National Electric Code, Article 430. If you're dealing with motors, you will spend a lot of time in this article, so it will become your friend. Tables 250 and 251 talk about running and starting currents for various sizes of motors, and they talk about inrush current, which currently is about 6x of full load running current per the NEC. A lot of manufacturers will give you a starting full load current. If we design our electrical systems properly, why do we care about inrush current? Well, we care because it's the secondary effects we want to avoid. You know, back in the day, the fan would start and the lights would dim. Well, that would be kind of annoying. We're concerned about the shaft torque. We don't want to, you know, overly stress that shaft if we can avoid it. Eventually, you know, it will fail. We have an upstream impact. And what I mean by that is a loss of diversity. If all of our motors have huge inrush currents, eventually those motors tie back into a particular electrical service, which would have to be sized or upsized accordingly. We can get things like air and water hammer. If that motor stops and starts quickly, we get noises, you know, from our air systems, from our water systems. And then we have to concern ourselves with overcurrent protection device longevity and conductor longevity. Again, if we're shoving a lot of current through these things very fast, LDI-DT, as you recall, we're going to stress these things as opposed to us providing current at a slower, steadier pace. So we got a couple of options here for starting motors. There's the time-honored method of just starting them across the line. Most small motors are started this way. You know, you flip a switch and the exhaust fan starts. They're low cost because there's really no cost, and they're simple start stop. You know, small fractional horsepower motors, they put a capacitor on the side of the motor, which helps that, and you're off to the races. Okay. We don't want a motor that starts and stops a lot because it's going to be stressful. But for a motor like a fan where we start it and it runs, we don't worry about it. Not a problem. So we get a little bigger motor, we got a little more of a problem. So they came up with something called a soft starter. Soft starter has been around a long time. And basically what it does is it starts the motor with reduced voltage and gets the motor to start to come up to speed in a little bit more of a controlled fashion. And then it switches up to full speed and then it takes off and runs. Again, these are good for larger motors running nearly continuously. Some places, some authorities having jurisdiction will require them above a certain horsepower because they don't want that large shock back into the electrical distribution system. A couple different types of soft starters: solid state, good, low cost, flexible. There's also the old mechanical time, which we used to call the delta, or the Y delta, or the star delta. Been around forever. The only disadvantage is there's a brief open transition as it switches, but typically for most applications, it's not a big deal. And then there's variable frequency drives, the B's and E's, latest and greatest. Total control starts at full voltage, great for all size motors, just gets expensive as they get big. They can be controlled remotely. They provide monitoring, provide energy efficiency, good things all around. Energy, they save energy, provide ideal performance, okay? How they work briefly: we put a constant frequency power in, we invert that, or sometimes we convert that to DC and then re-invert it back up to the frequency we want. And then we provide that to a driver section and we get variable frequency out. And as we learned earlier, if we adjust the frequency, we adjust the speed of our motor. Some things to keep in mind: the first two boxes in this graph, these are relatively easy and relatively standard. It's fairly small components, very easy to do, typical solid state stuff, not a big deal, fairly inexpensive. Where it gets expensive is on this backside. And these vary with the motor, and this is where the horsepower and the voltage come into play. And there's three or so different technologies that you'll see when you talk about big VFDs. SCR, silicon controlled rectifiers, insulated gate bipolar transistors, and insulated gate field effect transistors will all be used for these large driver sections. More than you probably wanted to know, but there it is. So here's a couple of pictures. The first one is a little 480 volt, 4 horsepower VFD. Very common. You see them hanging on the walls everywhere. This one does not have a disconnect or a bypass. That can be added separately. Versus the one on the lower left, and this is for that 4160 volt, 3500 horsepower motor that we looked at earlier. This thing it's the size of a house, literally. And if you look at, it's kind of hard to tell in this picture, but there's about 4 sections of cabinets there, and the 2 on the right are the control sections, and then the 2 on the left are the driver sections. We talked about total control, and where this really gets us some advantages is the fan laws, or the pump laws. We talked about flow is proportional to the shaft speed. Pressure, or head, is proportional to the square of the shaft speed. And then power is proportional to the cube of the shaft speed. So if you think about it, if we can reduce the shaft speed by 5%, we cube that savings in power. This is good stuff. We can save real money here with VFDs. We can also correct power factor with VFDs because they're not inductive when we connect them to the line. All they're doing is taking that AC and converting it to DC internally, and the power system doesn't see any of that. So they have a very high power factor. It's nearly unity in the most part. However, there's always a downside. VFDs can introduce harmonic distortions, which will affect that unity power factor. So the actual power factor has to take that into account, and you figure out what the total harmonic distortion is. That typically will come from the VFD manufacturer. You can do the math, figure out what your power factor is. And we have IEEE 519 to help us, okay? Covers harmonic distortions in electrical systems. This is something to pay attention to when you're specifying VFDs, is to make sure that the VFD is compliant with IEEE 519. So if we put all this together, what does all of this mean? Well, it means motor selection can be very detailed. In reality, I've been talking for about 35, 40 minutes here, and we've just sort of touched the tip of the iceberg when it comes to motor selection. It affects the entire electrical distribution. We have to read NEC 220 and understand it. Same with NEC 430. And we have to understand that there's a difference between high horsepower and high full load amperage. Okay, we need to make sure we know what we're talking about, because NEC is concerned with full load amps, not the biggest horsepower. Historically, we've always assumed that the biggest horsepower has the biggest full load amps, but if you have some bad motors, maybe that's not always the case. There are lots of selection components when we talk about motors. This graphic shows some of them. You know, what is the voltage? What is the horsepower? What's the frame, the class, the enclosure, the efficiency? Are we induction? Are we synchronous? How fast do we want it to run? What motor design type is it? Lots and lots and lots of things that we have to take into account if we're actually selecting a motor. This is a data sheet that I pulled off of a manufacturer's site. And this is the technical specs for their motor. And in this case, this is a simple single phase 2 horsepower capacitor start motor. And look at all of the things we have to choose, okay, or ignore. And you ignore them at your own risk. You know, what's the RPM? How many speeds does it have? What voltage does it operate? We talked about. There's our full load amps. We have a frame 215. So we went to the NEMA website. We could look that up and see what that means. Here's an interesting fact. Is this motor, which is designed to be 230 volts AC, usable at 208 volts? In this case, yes. What about below that? Nope, not so much. 60 hertz, standard service factor, and on and on and on. Here's our insulation class B. It's continuous duty, NEMA design L. It's a totally enclosed fan cooled unit we talked about. Which way does the shaft go? Well, this is interesting. This one seems to go both directions. And sure enough, make sure it's wired the right way. Nothing worse than having your fan run backwards when you start it up for the first time. How big is the shaft? How do you connect to the shaft? What kind of bearings does it have? On and on and on. This one's energy efficient, 80%. Okay. And it's got a 2-year warranty, all kinds of stuff. So what is this? About 40 things that come into play on selecting a simple single phase motor. 3-phase motor would be about the same, maybe slightly different. Lots to consider. VFDs, I think, are generally a good practice. The prices on them is coming down. They help us with our power factor. They give us complete control of our motors. I know several pump station operators, they have VFDs on all of their pumps, and rather than run one pump at 100% and one pump at 80%, you know, they run them both at 90% because they like to say that it increases the longevity of the pumps. Okay. Also gives them total control. Now, the advantage that we have, or some of us have in the commercial space, is we typically specify equipment, not motors. We're going to call up our favorite HVAC vendor and say, I need an air handler that provides 30,000 CFM at this static pressure, and I want to be able to control it because it's going to be a variable volume system, and you don't worry about what motor they put on it. Oh, you might tell them you want high efficiency. Okay. Same thing with a pump. We're going to specify a pump. We want to specify the flow, the head, the pressure, etc. And the vendor is going to provide us the pump and the motor. We don't have to worry about it because the motor always comes along for the ride. Now, I would assume, maybe not, some of us on the call actually would specify motors individually. And in that case, you're going to have to pay attention to all of this stuff in a lot more detail. For those of us that specify equipment, efficiency, you know, obviously voltage are really the biggies. You know, how efficient can we make our motor, make our equipment? So let's give an example here real quickly as we wrap this up. So let's assume we have a 3 horsepower, 460 volt induction motor at 80% lagging power factor. And real quickly, this is a 460 volt motor. Remember that equipment is specified at a lower voltage than service. So a 460 volt motor is intended to run on a 480 volt service. So a 3 horsepower motor, 80% lagging power factor. Rough order of magnitude motor cost, according to our good friends Google, is $1,000. Whoops. Nope, that was it. Okay. So we want to return our system power factor to unity because we have a really bad power company and they will ding us if we have a power factor below unity. So our 3 horsepower motor is 2.2 kilowatts real power. At 80% power factor, that means we've got 2.8 kVA of apparent power. We do the math, good old trigonometry, and we find out that our reactive power is 1.73 kilovolt amps reactive, okay? And our power factor angle is 36.8 degrees. So how do we make up for that 1.73 k bars? Well, we got to add that much leading power factor to the system. So we got some options. One is we can add just simply some power factor correction capacitors. It's a gray box, hangs on the wall. In this case, it's not going to be very big. You wire it into the system and it corrects the power factor. Again, rough order of magnitude of the component only is about $600. I didn't try to figure out how much it would cost you to wire it or install it, so on and so forth. And like we said, it hangs on the wall, it takes up space and provides no useful work other than it corrects our power factor. Another option would be to replace the induction motor with a synchronous motor. Okay. Now I'm assuming that we've already installed this piece of equipment, so we couldn't just order it that way from the factory to begin with. But in any case, it's about a $4,500 motor. Now in this case, our motor actually provides useful work. It's more efficient, doesn't take up any space, looks the same, all right, and does what we need it to do. The third option would be to install a 3 horsepower VFD. About $1,100. Again, I'm not taking into account a bypass or a disconnect or wiring or so on and so forth. It takes up a little bit of space. It does generate some harmonics, but it now provides us control. So maybe where we ran our fan full speed, maybe now we could run it at 90% speed and gain some advantages there. All right, I'm not going to factor that into the math we're about to do here in a minute, but it's a possibility. As we do each of these analyses, we have to figure out what's valuable and what's not. So the question is it worth the $3,500 to put the synchronous motor in place? I'm not going to do the $1,100 calculation because you'll get the idea. So it's 2.2 kW versus 2.8. We're going to assume 8,750 annual run hours. Your mileage may vary. And I'm going to assume you live somewhere like in Texas where electricity is relatively cheap and it's only 15 cents a kilowatt hour and there's no demand penalty. So you go through the math and you're going to save about $650 a year. So a simple payback says in 5 years, that motor is going to pay for itself. Depending on what this motor is connected to, air handler, for example, 5 years is nothing. We see air handlers in the field that are 15, 20 plus years old. So this motor would pay for itself 4 times over. That seems like a pretty good deal to me. Again, everyone's situation is going to be different, and I encourage everyone to do that analysis and see what makes sense, whether it's capacitors or induction motors. All that being said, I realize I haven't answered all the questions about motors and probably generated more than you had when you came in. And I appreciate that. And I will just leave you with, stop and look, do the math, think it through, and good motor success to you in your future.
All right, Jeff, thank you. That was great. A lot of terrific information. I have a couple of follow-up questions here for you. So let's start. You mentioned NEMA motors, NEMA premium motors. Where do NEMA premium motors come into play in specifications?
So that's a great question, Amara, and thank you. What we see more and more, especially in building spaces, is the International Energy Code comes into play, as well as LEED accreditation. And both of those things require very efficient electrical mechanical systems. And I think those are some really good places to consider spending a few extra dollars to get the premium efficiency, to show the increased energy efficiency of the facility, to get the LEED points, to meet the energy code. And in most cases, you can show the owner it has a payback that's reasonable for the life of the facility.
Okay, good. Thank you. The next question for you. This is kind of a multi-part question. What's the most common application in a building's engineered systems for motors? Are we looking at fire pumps or HVAC systems? And can you give me some background or examples?
Yeah, and again, another great question. And if you think about a typical multi-story commercial building, and we'll start at the ground floor, you're going to have a fire pump. That fire pump system is typically going to have two pumps. It's going to have the main fire pump when the building's on fire, but it's also going to have a jockey pump that keeps the system pressurized. Then we're going to have air handlers. We're going to move air through that building. We're going to have air handlers that take the air from the building and recirculate it. We're going to have air handlers on the outside that take air outside and filter it and cool it and bring it in. The air conditioning compressors or chillers are motors. The elevator in the building is motors. Some cases, those are DC motors. The kitchen area will have exhaust fans. The restrooms will have exhaust fans. So motors are everywhere. And if we want to get even more detailed, in our air distribution system, if we have variable air volume, or VAV boxes, those dampers will have motors on them to control airflow. So they're pretty prevalent throughout a commercial building.
So essentially everywhere. Okay, got it.
Yes.
All right, and last, so you touched on variable frequency drives and energy efficiency. How do you talk a building owner or a client into a higher priced motor or VFD? And what are some of those talking points for that conversation?
It's a great question, Amara. Thank you. And I think, the key is knowing your audience. And if you're talking to the maintenance guy who doesn't pay the bills, he's less interested than if you're talking to the building owner who's paying the bills about efficiency. But the way that I've found to be the most successful is to just do a simple pro forma and say, here's your first cost, here's your total cost of ownership, here's your simple payback. And then to sweeten the deal, if you can throw in some maintenance advantages, like we talked about, VFD, the motor is more efficient, he has more control. He gets data that he didn't necessarily get before to look at his control system and run his building better. So those are the types of things I think that work well. But realistically, at the end of the day, it's all going to come down to dollars. If you can show him that he can save, $1,000 a year, then that's much more attractive than not.
Right. Okay. Well, thank you, Jeff. That is all that we have time for today. And thank you for attending this education session, Back to Basics, Electric Motors. I'm your moderator, Amara Razgas, Content Manager with CFE Media and Technology. Thank you for attending this education session. This now wraps up our program. Thank you and goodbye.